Okay, yeah. Thanks for the introduction. My name is Kevin Knuckles. I'm a graduate student in the physics department here at Princeton. I work with Professor Ali Yazdani. And today I'm really excited to share with you all some of our newest results on magic angle twisted bilayer graphene, where we've uncovered kind of an unexpected series of topological insulators that are all gate tunable. So here's a general outline for my talk. I'll start with some introduction to this field of Moire flatband systems. This is a really young field within the field of two-dimensional materials. So I'll give some context for our work in light of a lot of really fast-paced work in this field. I'll talk about mostly this particular structure, magic angle twisted bilayer graphene, which is the one that I'm working on, which I argue has essentially the perfect ingredients for discovering correlated topological phases of matter. These are topological phases that are driven by electron-electron interactions. I'll talk about how we use the scanning tunneling microscope, which is a rather old tool in kind of an unconventional manner to explore many-body topology. And then I'll discuss how our results move forward and how we're using the new technique that we've developed in future problems. There we go. So I'd like to start with just like an early testimonial from the field that I'm in here. I work in solid state physics, which has been rebranded a couple decades ago to be condensed matter physics. This man on the left side you've probably recognized as Wolfgang Pauli, most notably known as one of the founders of quantum mechanics. The Pauli exclusion principle is named after him, and this was the work that he won the Nobel Prize for. But I think he's also known for giving kind of a scathing review of the early solid state physics. He's known for saying this thing, solid state physics is dirt physics. Sounds kind of like my parents, I guess. No, not actually, but yeah, it's difficult to hear some kind of founder of the theoretical constructs that you work on say such terrible things about your field. But I think that the main thing that he's getting at here is that although theoretical solid state research in the early days was really foundational and was really good about incorporating the new laws of quantum mechanics into understanding electronic phenomena of solids, experiment was largely muddy in a lot of ways. This resistivity is larger than this one. This heat capacity goes up and then down and then up again. It's kind of not as clean physics as maybe the nuclear physics that Pauli was most interested in. But I think that one of the most successful veins of modern condensed matter research and some of the most beautiful experiments that I know of that stand in direct opposition to this notion of dirty physics is the study of the many-body problem in the sense of the quantum Hall systems. So the many-body problem very succinctly states what is the quantum mechanical ground state of a large ensemble of interacting electrons. I have not 2, not 10, not 100, but an Avogadro number of electrons. They all see one another and they all decide in certain settings to collaborate into collective phenomena, which can be quite exotic. I think that some really nice clean systems to study this problem are the quantum Hall systems. This is a two-dimensional electron gas, many times made of gallium arsenide. Electrons are confined to a particular interface. They are placed in a very large magnetic field, something like tens of Tesla. And semi-classically, electrons in the bulk, they are kind of pushed by the Lorentz force into these small cyclotron orbits. And when these cyclotron orbits roughly get on the order of quantum mechanical scales, the energy levels get quantized. So here's some really beautiful data from a group at MIT who has been able to probe the spectral function of quantum Hall systems. And you can see there's a dispersive band right here that when you apply a particular magnetic field, a large magnetic field of 8 Tesla, you see that the spectrum becomes quantized into these flat bands, which we call Landau levels. So electrons living in these flat bands, they are macroscopically degenerate. They see one another in an extremely flat band. And so in this situation, Coulomb interactions dominate the system, and electrons will do everything and anything they can to mitigate this large Coulomb repulsive energy. So, in this very, very simple setting, this flat band system, the original flat band system, you can see that the system is extremely tunable amongst a wide spectrum of correlated phenomena. So here is plotted the longitudinal resistance of a two-dimensional electron gas, and this is the Hall resistance, this line up here. And you can see that as you tune the field, you're effectively tuning the filling factor of the Landau levels. So it's kind of like density. At many different magnetic fields, you see fractional phases with fractional excitations. These also are accompanied by fractional exchange statistics. Over here at 1/2, you get this emergent composite fermion C, which is built of electrons binding to two flux quanta. And then, over here at 5/2, you get this really unconventional source of superconductivity, a perspective topological P wave order. So, already you can see that this is an amazingly vibrant setting for studying electron physics. And it's largely just answering the question of, if electrons are left to their own accord, what do they do? What kind of ground state do they undertake? And so I think these experiments that have really pushed forward our understanding of physics of the many show that the physics of the many is rich and vibrant, that there are a ton of interesting exotic collective phenomena that occur in even the simplest of settings, that it's precise and absolute. This is in opposition to Pauli saying that, when you measure the Hall resistance, it is quantized to rational prefactors times fundamental constants of the universe. It's really beautiful this way. It's robust and universal, meaning that, largely this is tapping into like the topological order that you see in these systems, where it doesn't matter the shape or the size of the sample, it still shows this quantized anomalous Hall response. And that it's complex and extraordinary and completely unintuitive in many ways. So I think that generally, this is, the motivation that I have in working in this field is that the flat band systems, the original flat band systems of quantum Hall, were extremely fruitful. And suddenly, as of 2018, we have another route to something of a similar experimental setting. So the system I'm going to be talking about mostly is the system Magic Angle Twisted Bilayer Graphene, discovered by Pablo Herrero's group at MIT. It's very simple. Take two sheets of graphene and twist them by 1.1 degrees, and you create some sort of interference pattern of the two lattices here. And it's exactly at this 1.1 degree rotation that you get extremely flat band electronic bands where electron-electron interactions will dominate. We're deriving this structure from monolayer graphene, so I should talk a little bit about the electronic structure of monolayer graphene. Here is plotted a schematic of the band structure, so the energy versus momentum. And the band structure of monolayer graphene has a bandwidth of something like 10 electron volts, but its low energy physics is guided directly by these linear crossings, which we call Dirac cones. So there's a 0 point touching right here, and there's a linear dispersion, and most of the low energy phenomena is really aptly described by this linear dispersion. In addition, electrons in graphene come with 4 different flavors. Of course, there's 2 spin degrees of freedom, spin up and spin down. But in addition, there's also this valley degree of freedom, which tells me which momentum space point am I close to. And it ends up that it's very difficult to convert, electrons from K to K valley, just as it's difficult to convert electrons from spin up to spin down. So these are well-conserved quantities, good flavor degrees of freedom. If you take 2 sheets of graphene and you twist them with respect to one another, we should think about this in momentum space. So here is plotted in red is the top sheet of graphene, the Brillouin zone of the top sheet of graphene, and in blue is the bottom sheet of graphene. And when they're twisted with respect to one another, they create a finite displacement between the 2 valleys. We form this emergent, smaller, what we call a Moiré-Brillouin zone. These are the non-degenerate momentum space points that emerge in the system. And here's a schematic of the 2 Dirac cones that are just a small finite displacement away in the uncoupled picture. If we add in interlayer coupling, what that does is it couples 2 momentum space points right here, and through largely degenerate perturbation theory, this point right here opens up a gap. And so you can already see that like in this hybridized set of Dirac cones, there's a very small region in the center that is becoming very flat. And it ends up that at a particular angle, like 1.1 or 1.05 degrees, this region here becomes extremely flat and in some theoretical models, well separated from other bands. So this is already, you can see, emulating very much the flat band setting of quantum Hall. So I'd like to emphasize that there are two important consequences of this twisting. The first is that it's a method for flattening the electronic band from something like 10 electron volts by 3 orders of magnitude down to something like 10 millielectron volts. And then in addition, we create this superlattice potential, which we'll talk about admitting some integer number of electrons. So you can see that this superlattice has some kind of quasi-periodicity, and these regions where they're aligned, we call these AA sites. I'll show some STM topographs in a sec. We can think of loading up this Moire superlattice potential with 1, 2, 3, or 4 electrons per Moire unit cell. So by now, there's kind of a diverse zoology that's developed from this original platform of magic angle twisted bilayer graphene, where people are twisting all kinds of combinations of carbon, and then even some two-dimensional transition metal dichalcogenides. These are effectively semiconductors and that can be exfoliated and twisted themselves. And small, differences in the types of twisted systems give large differences in the observed correlated phenomena. So I'd like to emphasize there's one particular difference that's really interesting to me between the quantum Hall systems and these Moire flatband systems. And it's the notion of the presence or absence of time reversal symmetry. So in this two-dimensional electron gas, when I apply a huge magnetic field, I find that if I were to reverse the movie, play the movie backwards, a current that produces this magnetic field would start moving the opposite direction, and so the magnetic field would change directions. So largely, this system for band flattening in the quantum Hall regime is time reversal breaking, and it's explicitly so that we have to apply this large magnetic field to do so. In contrast, these Moire flatband systems, they form their flatbands in systems where time reversal is in many situations preserved. It's due to this, band hybridization, Brillouin zone folding. It depends on what you want to call it, but largely, I don't need a huge magnetic field in order to get very flat bands. And so I think that this comes with a couple of exciting prospects. You can ask, what kind of correlated electronic phases can we expect with this extra time reversal symmetry? I can think of two particular veins, and one of which is the main subject of my talk. So the idea is that maybe you can ask something like, what correlated phases arise that nominally break time reversal symmetry? Sorry, they nominally require time reversal symmetry. If I'm given this extra symmetry, are there phases that are just excluded from quantum Hall that I would never be able to recognize because I have an enormous magnetic field? And I think the most prominent of which and the most exciting that has really pushed our field forward is the discovery of superconductivity. Most kinds of superconductivity die in a magnetic field. And it is exactly the first observation of superconductivity from Pablo Herrera's group that has really got the Kinden's matter field excited. So you can see this is a plot of the resistance. It's a function of temperature. It's kind of plateaued here and then drops all of a sudden at around 1 Kelvin into a zero resistance state. In addition, when you look at some kind of gate tunable phase phenomenology, so this is temperature as a function of density, right around 2 holes per Moire unit cell, you find kind of a strong insulating phase. And then as you dope to either side of this insulating phase, you find a robust superconducting dome. So this is a really remarkable observation of gate tunable superconductivity and has spawned a bunch of theoretical work as well as some slow moving experimental work. In contrast, I can ask the question, what correlated electronic phases arise when time reversal symmetry is spontaneously broken? So if I'm giving the electrons this extra symmetry, are there phases that might arise where the electrons will want to lower their free energy by breaking this symmetry? And this is exactly what I'd like to talk about here is ferromagnetism is essentially one of the best examples of this. So I've split up, I guess, I've described the ferromagnets in two different senses. On the left side are spin ferromagnets. These are the most common case. These are the cases that you might think of in, say, iron, nickel, or cobalt, where time reversal symmetry is broken by the spontaneous alignment of spins. So at every atom, the unpaired d electrons, they point in one direction. If I reverse the movie, if I play the movie backwards, then these spins will point downwards, which will show that that state is not a time reversal symmetric. In addition, it's good to note that a small amount of magnetization in these systems is contributed from the orbital degree of freedom in the presence of spin-orbit coupling, but the vast majority of the magnetic field that you're feeling is the spin moment. In contrast, I talk about these things called orbital ferromagnets. These are based purely on the orbital degree of freedom of the electron, and they manifest as spontaneous persistent current loops which break time reversal symmetry. So electrons moving in small dissipationless current loops in the bulk, and you can even see that, say, if this electron is moving in some kind of orbit like this one, and this one is moving right next to it, then at the boundary, the left electron is moving downwards. There's a downwards pointing current, and then the right one is upwards, and so they cancel the current contribution in the center. But along the boundary, they sum up to some persistent current loop, which we call a chiral edge mode. So, you can think of, if you play the movie backwards, this chiral edge mode will start to point in the opposite direction. And so the magnetization of this orbital ferromagnet will switch. And so it's clearly breaking time reversal symmetry. It's also got some kind of topological aspect where there's this boundary mode. And this is exactly what's going to be tapped into in magic angle twisted bilayer graphene. So this type of orbital ferromagnet, a purely orbital ferromagnet, has not been recognized until the discovery of twisted bilayer graphene. So we have all the ingredients here. We've got extremely flat bands, which promote correlated electronic phenomena, which will want to break some kind of symmetry. And then we've got the incipient topological character that's been given to us through the Dirac-like dispersion of graphene. Each of these Dirac points is a singularity of Berry curvature. And if I take an electron and propagate it in the graphene band around one of these Dirac points, it will pick up a Berry phase, a geometric phase of pi. And so it's the name of the game is effectively somehow access this Berry curvature, gap these Dirac points, have them impart their Berry curvature upon this band, and then asymmetrically populate some number of bands in order to present a quantum anomalous Hall effect. So a little slower here, these Dirac points are protected by a composite symmetry, which we call C2T symmetry. C2 symmetry is just the rotation operator, the 180-degree rotation, and T symmetry is the spinless time reversal symmetry. And this composite symmetry, if it is present in magic angle twisted bilayer graphene, just as it's present in graphene, these Dirac points, these zero energy modes, will be protected, and all of the Berry curvature of the band is held in these Dirac delta spikes that are centered at each of these K points. So what we can try to do is we can try to break one of these symmetries in order to impart, a gap on these Dirac points. All of the Berry curvature will spread out onto the emergent Chern bands. And then if we asymmetrically populate some of these through electron-electron interactions, we'll find a magnetic phase, a topological phase. And so this was largely done by accident in the early days, 2 years ago, I guess. Where people took magic angle twisted bilayer graphene and they accidentally aligned it to the underlying boronitride substrate. Boronitride is a dielectric that's a single crystal that we use for basically all of our devices. And it looks like graphene, but it has boron atoms on half of the carbon sites and nitrogen atoms on half of the carbon sites. And so boron and nitrogen have different electron affinities. They present different electrostatic potentials, and when they're aligned to the graphene, they break this C2 symmetry forcibly. So when you do this, you can find that if you go to something like 3 electrons per Moire unit cell, so every aligned version of the Moire superlattice has 3 electrons, then at high temperatures like 5 Kelvin, you see the Hall resistance is largely featureless. And then as you cool down, you find this enormous hysteresis loop, a very, very large anomalous Hall effect that arises, emerges at low temperature. In addition, you can do some fun experiments to probe the non-local transport properties of this phase. I'd like to draw your attention to this one right here. So if I place some current into contact 5 and pull it out contact 4, and then measure the voltage far away, then you still measure this anomalous Hall response, which is kind of an essential signature of chiral edge mode. So this orbital ferromagnetic phase will have this. So this is really beautiful work from the Goldhaber-Gordon group at Stanford, which was largely followed up on by the Young group at UC Santa Barbara, where they made better devices, they're cleaner devices, and you can see at this same filling, the same density, you find a quantized anomalous Hall response. So at 0 magnetic field, the Hall resistance is h/e², fundamental constants of the universe. And they're doing this largely from the same prescription that I've described before, is take the bands of magic angle twisted bilayer graphene, break one of the symmetries by hand to impart your Berry curvature into these emergent Chern bands, and then partially fill the flat bands and hope the electrons take the bait and valley polarize through electron-electron interactions. So when I sum up the Berry curvature of these filled bands, I get a net Chern number of 1, which gives me the anomalous Hall response that's quantized here. Since then, there have been a number of experiments on other platforms that have seen quantized anomalous Hall responses or nearly quantized anomalous Hall responses. But largely these magnetic topological phases in Moiré systems have been mostly reported in device geometries that purposefully break a spatial symmetry of the graphene system. So I think this is where our work deviates, in which our main experimental result is the idea that strong electron-electron interactions alone can produce new correlated topological phases in magic angle twisted bilayer graphene. I don't need the Bohr nitride alignment. I don't need to break any symmetries by hand. And these topological phases will do so in they'll break the Dirac points, they'll gap the Dirac points in a really odd way by breaking time reversal symmetry instead of the rotational symmetry of the system. So we're performing these experiments using the scanning tunneling microscope. This is the newest addition to Ali's suite of instruments called the ultra low temperature scanning tunneling microscope, which I helped build with a number of my lab mates. It's a dilution refrigerator STM. So our base electron temperature is something like 180 millikelvin. This gives us roughly a 50 micro electron volt energy resolution. We've got a nice vector field with a 9 Tesla out of plane and 1 Tesla in plane. And then a couple of other amenities that make experiments easier or harder depending on the day. We're building these devices as everyone is, or nearly everyone was at one time, using this method called the tear and stack method, which was developed by Emmanuel Tutuk's group at Texas. The idea is that if the magic angle condition is so sharp, it's such a sharp resonance at 1.1 degrees plus or minus 0.1 degrees, you'll need to be able to reproducibly twist by these angles in order to make any progress in this field. And so the idea is take a large sheet of graphene, this is all single crystal, and tear it in the center. And if I use some polymer pickup method, I grab some boron nitride, and then I grab half of my graphene, then the half of the graphene that I have on my polymer and the half of the graphene that's left behind, the two sheets are lattice aligned. And so their relative twist angle is 0. And so if I add a relative twist between the two when, in the middle of the pickup method, then you can reasonably reproducibly get close to the magic angle. So this is a really nice technique to do so. And I think people have been optimizing this through cutting or through a variety of other methods that are largely based on this idea. So if you do topographic imaging of these magic angle twisted bilayer graphene devices, you should see something like this Moiré periodic structure. So this is a schematic taken from Quanta magazine that shows nicely that there are some regions in the Moiré superlattice that you can see the two lattices are aligned, and then some regions where they're out of alignment, and some regions that are, some kind of rhombohedral stacking, which is exactly what you see in real data in SDM topographs of magic angle twisted bilayer graphene. We'll refer to these bright regions right here, which are graphene aligned in both layers as AA sites. We'll refer to these dark regions here as AB sites or BA sites, where it's exactly out of phase. And then the middle regions between the two AA sites are these things called bridge sites. Largely, we'll be taking a lot of spectroscopy in these bright regions because the flat bands of MATBG are largely localized to these AA sites. So some basics of gate-tunable spectroscopy on these devices. I'm using the STM where we bias the sample and then we measure the tunneling current through a tip that is something like half a nanometer away from the surface. This graphene is sitting on top of insulating hexagonal boron nitride, which acts as a dielectric. It's sitting on insulating silicon dioxide, which is also a dielectric. And then that's sitting on top of silicon, which is degenerately doped. So this is our metallic gate. And we'll measure the current as a function of sample bias and of gate voltage. Gate voltage is changing the carrier density. So, some very basic characterization is if I apply a very large positive voltage to the back gate, I completely fill the flat bands and they show up as two very sharp peaks in DI/dV. This is the differential conductance, which in the single particle limit is proportional to the local density of states. I can do the same thing on the negative side where I depopulate the flat bands and they appear as very sharp resonances here. So largely we'll be looking at data in a color plot scenario where we slowly increment the backgate. This slowly changes the carrier density and we take spectra like this and form some kind of color plot where blue means no conductivity, many times meaning a gap, and red means high conductivity, meaning a peak in the local density of states. And again, we'll be filling this Moire unit cell with 1, 2, 3, or 4 electrons, or with -1, -2, -3, or -4 electrons, which we call holes. And 0 represents like if you didn't apply any voltage. That this is we call this charge neutrality. Cool. If you cool down the sample and you look at spectroscopy as a function of density, in magic angle twisted bilayer graphene, you'll find that there are a number of gaps that open up at low temperatures, something between 4 electrons and 2 electrons per Moire unit cell, and then something between -2 and -4 electrons per Moire unit cell. Some of these gaps are seemingly related to superconductivity, which I won't focus on today, but what I do want to focus on are the gaps that emerge with increasing magnetic field, the gaps that move systematically with magnetic field. So if you apply, go from 1 Tesla to something like 6 Tesla, you find there's a number of gap phases. These are blue states, 0 conductance at the Fermi level that appear in the upper flat band. There are a bunch that appear in the lower flat band, and then there are a bunch in the middle, which are well characterized as the Zeroth-Landau levels of twisted bilayer graphene. So these are completely unexpected, and the center ones are largely expected. So we'll use a lot of our intuition from the center gaps in order to derive some properties of the outside gaps. So let's focus on these center gaps here. Here you can see in the local density of states, you can see, or the differential conductance, you can see 2 features that appear in white. These are shown in line cuts to the right side as well. So 2 sharp peaks in local density of states that represent the 2 4-fold degenerate Zeroth-Landau levels of magic angle twisted bilayer graphene. And as I gate one of these peaks to Fermi, it will split a number of times. In fact, split 3 times before exiting Fermi. And then the other peak splits a number of times as well. So this is largely expected from just kind of a basic characterization of the degrees of freedom of the system. We expect there to be 8 degenerate Dirac cones in the system, 2 for spin, 2 for valley, and 2 for this now emergent Moire valley or corner degree of freedom, which kind of comes from the fact that there are 2 sheets of graphene. So we expect there to be 8 degrees of freedom, and we can see from spectroscopy that there is a splitting of 2 peaks even before these Landau levels get to Fermi. So this is a single particle splitting, and then as this peak is gated to Fermi, it undergoes a number of splittings that only occur at the Fermi level. So we know these need to be correlation driven. And this is largely an extension of quantum Hall ferromagnetism that is observed in graphene. Very briefly, it's the understanding that in a system with of Landau levels, it's more energetically favorable. Instead of filling 4 different populations, 4 different flavors of electrons 1/4 of the way, it's more energetically favorable to fill a whole flavor all the way and to empty all of these flavors. It's a way to lower the free energy of the system. So these, splittings here, these are interaction driven, and then there are also some single particle gaps here that we'll take a look at in a sec. So if you do some basic magnetic field response characterization of the Zeroth-Landau level, you find that as you increase the magnetic field, these gaps move away from charge neutrality. So they kind of emanate all from this one point, which is exactly what a Landau fan would show you in transport, is that Landau levels carry Chern number 1. And so gaps between Chern Landau levels will disperse with particular linear slopes. But in addition, tunneling spectroscopy tells us a little bit more than what a Landau fan would tell you. It tells us that these gaps at -4, 0, and 4, that's 4, 0, and -4, these are single particle gaps. And we know this because it's associated with a gap-like structure before the system is gated to Fermi. So even when the Landau levels are far away from the Fermi level, we can see a gap between them and other states here. Whereas these states right here only emerge at the Fermi level, and so that we know that these are many body gaps, and these are well quantified as quantum Hall ferromagnetic gaps. In addition, we see these other gaps that occur at other fillings in the flat bands. I'm showing 2 particularly nice examples at 6 Tesla. This one near 1 electron per Mori unit cell, this one near 1 hole per Mori unit cell. And we can also see that these are correlation driven. You can see that the flat band with a small zero bias suppression is pinned to the Fermi level. And as I remove electrons from the system, eventually I get to some magic filling, magic carrier density, where the system gaps away. It opens up to a very blue region. This is an insulating phase, and then closes up at the Fermi level. So this is clearly an interaction driven system, and it's largely unexpected. So I think the key observation is that we'll tap into the Landau level in intuition, which in plot as a function of magnetic field. Landau levels, they move away from charge neutrality, and they move so with quantized slopes. But also these other gaps move away from charge neutrality, and so we'll use this formalism straightest theorem in order to analyze the topological nature of all of these gaps in total. So very briefly, this is an important concept that we'll be using to analyze the origin of these gaps is straightest formula or straightest theorem, which tells us that the charge density of a topological insulating phase changes with magnetic field, and it does so at a rate that's equal to its quantized Hall conductance. This is a really succinct way to say that as a topological insulating phase is placed in a changing magnetic field, charge accumulates in the bulk at some particular rate that's guided by its Chern number. So very briefly, if I have some system that has an anomalous Hall response, a quantized anomalous Hall response, its Hall conductivity is characterized by its Chern number times fundamental constants of the universe. In the presence of this Hall conductivity, by Maxwell's relation, I mean Maxwell's equation, we know that a changing magnetic field will cause a curl-in-E, so a solenoidal electric field that points around this direction. Because the system has a Hall conductivity, the electric field that points around this way will pull current into the bulk here. It's a transverse transverse conductivity that pulls electrons into the bulk. And this charge will accumulate in the center. And it does so such that the change of the density as a function of magnetic field is equal to the Chern number divided by, again, fundamental constants of the universe. So this is really fantastic that when we plot topological gaps, the density of a topological gap as a function of magnetic field, we should be able to read off lines, and the slope of the line is just the Chern number. So if you do this with, proof of concept, just do it with the lambda levels. Lambda levels have Chern number 1. And so what we should be able to do is plot the density in some more normalized units. These are electrons per Moire unit cell, and plot the magnetic field in some normalized units, the fluxes per Moire unit cell. And we find that the slopes match up with exactly the Chern numbers that we'd expect from just a basic understanding of the zeroth lambda level. So Chern numbers 4 to -4 emanate from charge neutrality, and then there's some higher lambda levels that we saw in one device. We can try to use this structure on these anomalous gaps, and I think that this is really fruitful because the fact that we're using spectroscopy to analyze these gaps gives us a bit more of a handhold on where they're coming from. The idea that spectroscopy shows no association with a single particle gap feature. It's just the flat band pinned to the Fermi. It gaps at Fermi and then closes at Fermi. Tells us that this must be a many-body gap feature. In addition, we know that these are not integer correlated insulating phases because they don't occur at nice filling factors of 1 hole or 2 holes per Moire unit cell. So there was a lot of work that studied some topologically trivial insulating phases. This cannot be that one. In addition, we can watch this gap move as a function of magnetic field, and it does. And so we know that this must be a topological gap by Strata's formula. So these two quantities here, knowing that it's a many-body gap and knowing that it's a topological gap is kind of unprecedented, and it's a really nice way to use scanning tunneling spectroscopy as a probe for many-body topological phases of matter. So if you do this, the same prescription as we did for the zeroth lambda level, just do it for the other gaps that we see. We find that they also disperse with quantized slopes. And we find topological insulating phases, they're gap phases, and in this case, because they have finite Chern number, we'll call them Chern insulators. Chern insulators with Chern number 3, 2, and 1 emanating from 1, 2, and 3 electrons per Moire unit cell, and then of course the particle hole conjugates of all these. So when I talk about these Chern insulating phases, I really do mean some large sheet of magic angle twisted bilayer graphene with a couple of chiral edge modes. And it's exactly these chiral edge modes that through the short derivation that we discussed in for Strata's theorem that will pull current into the bulk. So current will accumulate according to the number of chiral edge modes, which gives us the Hall conductivity, and it will accumulate 3 times faster in a Chern 3 insulator as it will for a Chern 1 insulator, and that's why the density changes at 3 times the rate of in a Chern 3 insulator than a Chern 1 insulator. So these are the 6 states that we've uncovered in MATBG, and they're all gate tunable. So if I move to some gate voltage that they don't exist, it's largely a metallic phase, which is really fantastic. In total, we've measured 3 devices and plot them all here as a summary, and you can see that the data unequivocally follows particular strata fitting lines of 3, 2, 1 from nu equals 1, 2, 3, and a number of other groups, mostly transport with the exception of Stefan Naj-Purge at Caltech, who also does STM, largely report similar findings in unaligned MATBG. So with the time that I have left, I'd like to spend it on discussing where these Chern insulators may be coming from. Let's bring us back to the fact that these Chern bands are a product of the incipient topological character of graphene, which comes from the Dirac points. Again, these Dirac points are protected by this composite C2T symmetry. And largely, the existing body of work has shown that if you can break one of these symmetries, namely C2 symmetry, by aligning the system to a bore nitride substrate, then you impart this Berry curvature onto some Chern bands, and then you asymmetrically fill these Chern bands to get a quantum anomalous Hall effect. So this looks like a staggered mass term that opens up a mass gap at the Dirac points in real space, where every other sublattice is experiencing a different sublattice potential. In contrast, we postulate that the bands of magic angle twisted bilayer graphene are split. The Dirac points are gapped by breaking time reversal symmetry in the form of what we would call a Haldane mass term. So in the staggered sublattice potential mass, a gap of equal magnitude opens up in the two valleys, and in a time reversal broken mass term, equal and opposite mass gap opens up in the two valleys. So you can essentially think of this as the momentum space analog to the real space C2 symmetry, where in the K valley we open up maybe a negative gap, but in the K prime valley we open up a positive gap. And I should emphasize that this setting would be nice because it would be, it would jive very nicely with existing literature, but our observations are irreconcilable with this notion, because we see particularly Chern +3 and -3 insulators, which can only be explained by a time reversal symmetry breaking mass. So I think kind of sparing the details here because it gets kind of complicated. With a Haldane mass in place, you can go back to Haldane's original paper. I have a backup slide if people have questions about this, but you can go back to Haldane's original paper, and he predicts that in a setting where time reversal symmetry is broken, you should be able to measure the sign of the time reversal mass breaking term via the Zeroth lambda level. So in a time reversal broken system, the Zeroth lambda level will appear very asymmetric. It will appear either very, very close to the valence band or very, very close to the conduction band, depending on if the mass is positive or negative. And in fact, what we need for the Chern bands to, the Chern bands that we need to give us the correct topological insulators, the Haldane mass should be negative in the upper band and should be positive in the lower band. And we exactly see this lambda level asymmetry where the lambda levels are very close to the valence band Van Hove singularity, and then they cross over and they effectively merge with the conduction band Van Hove singularity, giving us a sign switching time reversal breaking term. So in this case, when the mass gap opens one particular way, I fill these 4 Chern +1 bands and 1 Chern -1 band. And so the total sum is +3. This is a Chern 3 insulator in the upper band. I reform the Dirac points or reform the Zeroth lambda levels. And then in the lower flat band, it needs to invert. You can see that the Chern numbers are all opened up in the opposite direction. So the time reversal breaking mass needs to invert over here to give us the Chern -3. Largely, the details of a much better treatment, a much more thorough treatment, is given in a series of papers written by Biao Lian, who recently became a professor in the physics department, and Andre Bernavig, where they use analytics and numerics and a lot of other techniques to explain that electron-electron interactions will try to break time reversal symmetry to produce a Landau fan diagram that looks a lot like this. So we expect from this model, if you want to spend a little bit more time looking at this, we expect a charge neutral fan and then a Chern 3 insulator, a Chern 2 insulator, a Chern 1 insulator emanating from 1, 2, and 3 electrons per Mori unit cell at high fields. And then they predict a couple of low field transitions that we have not observed. So conclusion, I'd like to say that correlation-driven Chern insulators in MATBG are competitive low-energy states, and we really are able to stabilize them as the true ground state with the application of a weak magnetic field. In these samples, we do not see the Chern insulators at zero magnetic field, but we believe that they're competing with they may be competing with a number of zero field states, and with the application of a small magnetic field, we're able to stabilize them. So a bit of discussion. Our work stands to show for 2 particular sources of novel physics. The first is that we're presenting essentially a new mechanism for engineering topological phases of matter. And it's exactly through this idea that electron-electron interactions will collaborate into some kind of collective phenomena. They'll collaborate to mitigate Coulomb interactions and break some kind of symmetry. So if a system is given some incipient topological order, but it's largely inaccessible, there are settings where electrons will access it for you, which is really a beautiful way to try to create these topological phases. In addition, we present this new approach of using the STM in a rather unconventional way to identify many-body character of phases through spectroscopy, where we can see gaps only opening at the Fermi level or gaps that have already preformed away from the Fermi level to determine single particle many-body character. And then we can also determine its topological invariant by performing this experiment at a series of magnetic fields, plotting them under some normalized conditions, and just reading off the slope, that the slope gives us the Chern number of these insulating phases. So with that, I'd like to thank my collaborators, Professor Biao Lian and Andre Bernavig, for their theoretical support and a number of theoretical papers that much more thoroughly treat this problem that came about in the past several months. I'd like to thank my experimental collaborators, Dylan Wong and Mitchell Oh, their postdocs in Ali's group, and I've learned so much, essentially everything that I know about STM from these two guys. And then I'd like to thank, of course, my advisor, Ali Yazdani, for making all this work possible. Thank you.
Thank you, Kevin. That was wonderful. If anyone has any questions, feel free to, yeah, just jump in and ask them.